Refraction of light at spherical surfaces. Today we are going to study about refraction of light at spherical surfaces. So before going into it, we should know coordinate geometry sign convention for measuring distances and lengths. See, what is the purpose of knowing coordinate geometry sign conventions? See, in order to obtain some formula for position and sizes of real and virtual images that are formed by convex and concave lenses, we have to adapt a common convention for giving sign, that is positive or negative. So there is a set of rules. Usually we prefer coordinate geometry sign convention. Okay, so hope you understood why we are talking about coordinate geometry sign convention. Just look at this diagram. See, I have taken a convex lens. So this is the optical center. Okay, so in this sign convention, the optical center of the lens is taken as the origin, and this is the principal axis. The principal axis of the lens is the x-axis. Okay, again, a line passing through the optical center and perpendicular to the principal axis. So we have considered this as x-axis. So the line perpendicular will be our y-axis. Now, all the distances are measured from the optical center. So the distance measured to the right of the optical center. See, this is the optical center, this is right and this is left. So from here to this side, the right is taken as positive. The right is taken as positive and the left to the optical center is taken as negative. The left is taken as negative. Okay, again the next part, the distance measured upward from the principal axis is taken as positive, and those measured downwards are taken as negative. This is coordinate geometry sign convention. Okay, again I want to tell you one thing. You keep that in mind. That is very, very important as far as sign convention is concerned when you are doing numericals. See, the direction of incident ray is taken as positive. The direction of incident ray is taken as positive. So this is the thing you have to remember. Okay, refraction at a convex spherical surface. So we are going to derive the relation n2 by v minus n1 by u is equal to n2 minus n1 by r, where n2 is the refractive index of denser medium and n1 is the refractive index of rarer medium. V, the image distance, u, object distance, and r is the radius of curvature. So let us see how to derive this relation. And this relation is very important, and board exams they ask you to derive, or they ask you to solve numericals related to this formula. Even in competitive examinations they ask this. So just try to understand, and it is very, very easy. Okay, see, we are going to learn refraction of light at convex spherical surface. Convex spherical surface. So let S, P, S dash be a convex spherical surface. S, P, S dash means convex spherical surface. Actually, it is separating the rarer and the denser medium. This one is rarer medium. So the refractive index is N1. And this is the denser medium. See, I have extended this line. So this is denser medium. The refractive index is N2. So N1 is the refractive index of rarer medium and N2 is the refractive index of denser medium. Now I am keeping a point object along the principal axis. See, this is the line. This is the principal axis that is passing through the pole. This is the principal axis. So I am keeping a point object. Now, this point object is incident at point M on the spherical surface. OM is the incident ray. Now, I already taught you for a spherical surface, how will you draw the normal? Through the center. Through the center. So through the center, this is the normal. So what will be this angle? The angle incident ray makes with the normal is called angle of incidence. So I is angle of incidence. Okay. Again, see, when light strikes at a spherical surface, see, when it travels from rarer to denser medium, see, this will be the direction of the refracted ray and the image is formed at I. Image is formed at I. If there is no spherical surface, the light would have traveled in this way. But due to refraction, the image is formed at I. Now, see, this is P is the pole. P is the pole. Pole is the center of the refracting surface. P is the pole of the refracting surface. And C is the center of curvature of the sphere. That is, our lens was part of a sphere. So, C is the center of curvature. Through that, the normal is drawn. Through that, the normal is drawn. Now, we have PC is the radius of curvature. So one more time, I'm going to explain all these symbols. N1 is the refractive index in rarer medium. N2 refractive index in denser medium. P the pole. C center of curvature. And PC radius of curvature. I is the angle of incidence. Then this angle is R. R is angle of refraction. R will be angle of refraction. Okay. Now, PC is the radius of curvature. So, this is R. PC is R. PC is R. Radius of curvature. And PI is V. And what is OP? OP is U. So if you apply the sign convention, I told you the direction of incident ray is taken as positive. So this is the direction of incident ray. Direction of incident ray. Therefore, R and V are positive and U is opposite to the direction of the incident ray. So U is negative. Okay. So if you can draw this diagram correctly, very easily you can derive the relation. But very important thing before deriving this relation is the assumptions we make. We make certain important assumptions before deriving this relation. So let us see what are the assumptions. See, the first assumption is the object is a point. Point object is taken. The first assumption is we are taking a point object. The next one is all rays are paraxial rays. What are paraxial rays? See, if you draw a lens and the principal axis, the rays that are close to the principal axis. So this is principal axis. The ray that are close to the principal axis and parallel to the principal axis, they are called paraxial rays. Why we are taking paraxial rays? Because paraxial rays forms very small angles. Angles are very small. These paraxial rays forms very small angle. Again, if the rays are far at the edge of this lens, we call it as marginal rays. We are not considering the marginal rays. We are only considering paraxial rays. So this is our first assumption is point object. Second assumption is all rays are paraxial. The third one is the lens of small aperture is taken. What is an aperture? See, the refracting surface. Okay, this is the effective diameter of this is the refracting surface. This is called aperture. A very small aperture is taken. Again, if you see in this diagram, small part of a large spherical surface. So if this is a very large spherical surface, a small part is taken. It will not be very much spherical. A small part of a large spherical surface is taken. One more time, what are the assumptions we are making? A point object we are taking. All rays are paraxial rays. The purpose of considering paraxial rays is that they form very small angles. That will be useful for our calculation. Small aperture and small part of a large spherical surface is taken. So these are the assumptions. Okay, for deriving the relationship, let us make some construction in this diagram. Okay, let us drop a perpendicular from M to the principal axis MP dash. So MP dash will be the height. So MP dash is height. Again, let the angle of this incident ray let the incident ray makes with the principal axis be alpha, and this angle be beta, and this angle be gamma. So all this we are doing to make a calculation. Okay, let's start the derivation. So in this diagram, if you take triangle OMC, see, I is the exterior angle. Exterior angle I will be equal to the sum of interior opposite angles alpha plus beta. So I have written here exterior angle I is alpha plus beta. Again, in triangle CMI, exterior angle beta will be equal to the sum of R plus gamma. R plus gamma. So this implies R will be equal to beta minus gamma. So we got one equation for I and again an equation for R. We know by Snell's law, what is Snell's law? Sin I by sin R will be equal to N2 by N1. So this can be written as N1 sin I will be equal to N2 sin R. Again, we have taken for small aperture. Am I right? In the assumptions I told, small aperture, sin I can be equal to I and sin R will be equal to R. So this equation becomes, so what do we have? We have N1 I will be equal to N2 R. So see, in this equation I am going to substitute the value of I and R. So what will happen? So we will get N1 alpha plus beta will be equal to N2 beta minus gamma. Okay, so this is the equation we got after substituting the value of I and R. See again, see, tan alpha is equal to, what is tan alpha? Perpendicular by base. See, perpendicular by base. It is h by u. But according to sign convention, u is negative because u is opposite to the direction of incident ray. This is u. U is opposite to the direction of incident ray. And this aperture is very small, so P dash is very close to P. P dash is close to P, so we can neglect P dash. Instead of P dash, we can write P. See, this distance is very small. P dash is very small. So you can write h by u, because students, you may ask me, sir, OP is u and h by OP dash will come in this right triangle. Right. But since we are taking very small aperture, P dash is negligible, very small. So instead of h by OP dash, we can take h by OP. We can take, see, h by OP dash can be written as h by OP. Okay, tan alpha. Are you understanding? So we can apply this for all the angles. And again, what is tan beta? Tan beta is perpendicular by base, that is h by r. R is positive. Again, r p dash c, we can write pc. Tan gamma, what is tan gamma? It is h by v. Okay, r and v are positive, u is negative. Okay, I have already told you r and v positive and u is negative. Okay, now see, for small aperture, tan alpha will be almost equal to alpha, tan beta will be almost equal to beta, and tan gamma will be almost equal to gamma. So we are going to substitute in N1 I is equal to N2 R. So that is N1. What is I? alpha plus beta, that is n2 beta minus gamma. So we can substitute the value of alpha, beta and gamma. See, tan alpha, so what is our alpha? Alpha will be minus h by u, beta will be h by r and gamma will be h by v, because tan alpha is almost equal to alpha. Okay, so n1, what is alpha? Minus h by u plus beta h by r, that is equal to n2. What is beta? H by r minus h by v. So in this equation, you can take h outside. So n1h minus 1 by u plus 1 by r will be equal to n2h 1 by r minus 1 by v. So you can cancel h. You can take n1 inside. Minus n1 by u plus n1 by r will be equal to n2 by r minus n2 by v. We can bring this n2 here. So n2 by v minus n1 by u is equal to n2 by r minus n1 by r. So this can be written as n2 by v minus n1 by u, that is equal to n2 minus n1 by r. So this is the required relation. Okay, this is the required relation we have derived, where n2 is the refractive index where the incident ray enters. So n1 is the refractive index where incident ray is coming, n1, okay, and n2 is incident ray enters. Okay, so v is the image distance and u is the object distance. So this is the required relation. Hope you understood this relation, and this relation is very, very important.